Stellar black holes. These are the most common black holes in the universe, formed when a massive star reaches the end of its life and collapses under its own gravity. After a supernova explosion throws off the outer layers, the core compresses so tightly that not even light can escape. They are usually a few to tens of times more massive than our Sun, and they drift through galaxies, sometimes pulling in nearby gas or even companion stars. What makes them important is that they represent the natural endpoint of stellar evolution for heavy stars, giving us a direct link between life cycles of stars and extreme gravity. Intermediate mass black holes. These black holes fall between stellar and supermassive ones, with masses ranging from hundreds to thousands of suns. For a long time, they were mostly theoretical, with only indirect evidence suggesting they exist. They may form from repeated mergers of smaller black holes in dense star clusters, or from the collapse of unusually large stars. Their importance lies in possibly explaining how supermassive black holes grew so large, acting as a missing step in the cosmic scale. Supermassive black holes. These giants sit at the centers of most galaxies, including our own Milky Way, where Sagittarius A star resides. They can contain millions or even billions of times the mass of the Sun, yet their origin is still not fully understood. Some may have grown from smaller black holes merging and feeding over time, while others could have formed very early in the universe. Their immense gravity shapes entire galaxies, controlling the motion of stars and sometimes powering bright quasars when actively feeding on matter. Primordial black holes. These are hypothetical black holes thought to have formed not from stars, but from density fluctuations in the early universe shortly after the Big Bang. If regions of space were dense enough, they could have collapsed directly into black holes of various sizes, some possibly as small as a mountain. Although none have been definitively confirmed, they are fascinating because they could help explain dark matter or provide clues about the conditions of the early universe. Rotating black holes. Also known as Kerr black hole, these black holes spin due to the angular momentum of the material that formed them. The rotation drags space-time around with it in a process called frame dragging, creating a region outside the event horizon known as the ergosphere. In this region, objects cannot remain still and are forced to move along with the spin. This rotation can even allow energy to be extracted from the black hole, making them key to understanding high-energy cosmic phenomena. Non-rotating black holes. These are described by the simpler Schwarzschild black hole model, where the black hole has mass, but no spin or electric charge. In reality, perfectly non-rotating black holes likely do not exist, since most collapsing stars have some rotation. Still, this model is crucial because it provides the foundation for understanding black hole physics, with a perfectly spherical event horizon and a simpler structure that helps scientists build more complex theories. Charged black holes. The two types of charged black holes is our Reisner-Nordstrom black holes without spin and Kerr-Newman black holes with spin. These theoretical black holes carry an electric charge. In practice, they are unlikely to exist in nature for long, since surrounding matter would quickly neutralize the charge. However, studying them helps physicists explore how gravity interacts with electromagnetism, revealing deeper connections between fundamental forces. Binary black holes. These are systems where two black holes orbit each other, gradually spiraling inward over time. As they merge, they release powerful gravitational waves, ripples in spacetime first directly detected in 2015 by LIGO. These events provide a new way to observe the universe, allowing scientists to study black holes not through light, but through the vibrations of space itself.